All right, I'm back. This is going to be elastic collision analysis video number 6, where it is going to be shown once again that momentum can only be conserved when we treat it as a vector. In other words, when we treat the opposite direction as a negative value. And also, it's going to be shown that kinetic energy is also conserved. Whereas if we don't treat momentum as a vector, but as a scalar, then we are always going to end up with lots of free extra energy or momentum. So we're going to be analyzing this particular experiment video, which is going to be done by a Dutch professor. He's going to speak Dutch, which is also my native language. I can understand him perfectly well. It's going to start with saying the masses of the cards.
Karretjes wegen, zullen bij 275 gram. Blauwe.
So he says 275 gram, which means 275 grams for both the cards, the red card and the blue card individually. So mass 1 is going to be 275 grams. I have to change this again. So 275 grams. Mass 2 is going to add a bar of 250 grams. I have to skip a part now. Yeah, here. So a bar of 250 grams. So we have mass 2 is going to be 525 kilograms. Okay. There we go. Then it's going to show the chart. Hold on. Yeah, so here we have, he already did 3 runs. And here they are all shown at the same time. So he's going to filter the last one. Oh, hold on. Yeah, he done it again. This is a new run with the small mass against the big mass. And now he's going to filter the latest run. There we go. So this peak is the initial velocity. After collision, this is the reflection velocity, the card bouncing back. And this is the second velocity, the big mass velocity after reflection. Now he doesn't say the velocities, so we are going to have to look at it ourselves. So I took a print screen and then try to see what the velocities are. So here we have the 0 line, and each block is 0.05. So we have 0.05, 0.10, 0.50, 0.20, 0.25, and all the way on top we have 40, 45, 50, 55, and it seems to me that it is going to be 56, 57. If you disagree with me, you can check it yourself, but it really looks like 0.57 meters per second. That's going to be the initial velocity. And then the recoil, when it reflects back, its velocity is way down here. So this is minus 0.15. And it looks to me like, what did I wrote? So 0.17 and a half, let's see. Looks like, so 0.15, 0.16, 0.17, and it's like in between 0.17, 0.18. That's what I think. I have to use my eyes now. I cannot perfectly tell it, but it looks like minus 0.17 and a half. Looks like, it's not as like, but here we have more accurate chart. So I'm going for 0.17 and a half for the recoil, and the big mass after collision is over here. So here we have 0.35, 0.36, 0.37, and then 0.38. It looks like in between 0.37 and 0.38. So 0.37 and a half. I have chosen those numbers as the velocities. Then we're going to, so these are the results, the experimental results. Now we're going to do the theoretical predictions. The theory predicts that after collision, the recoil velocity will be 0.178 meters per second. And the result is 0.175 meters per second, which is extremely close. So that would be a pretty good match, very good match. The second velocity, the big mass after collision, the prediction is 0.39 meters per second. The result is 0.37 meters per second. So a little bit off, pretty close, 0.37 versus 0.39, not a gigantic difference. Now let's take a look at the momentum. The initial momentum of part 1 coming in before collision is 0.156 kilogram meters per second. Then the collision, the part 1 after collision reflects back with a momentum of minus 0.048 kilograms meters per second. Part 2 has a momentum after collision of 0.196 kilograms meters per second. When you add those together, and again, when we treat the opposite direction, when we give it a negative value, okay, so a negative momentum plus a positive momentum, right? If we do that, then it equals 0.148 kilograms per second, which is a difference. So the difference now between the total initial momentum and the combined, so the difference between the total initial momentum before collision and the combined momentums after collision has a difference of 6.9%. Whereas, according to draft science, momentum is not a vector, it's a scalar. We have to, directions don't matter, they always are positive no matter what. So we always have to add them together. If we do that, then we have a momentum of 0.244 kilograms meters per second, which is an increase of 53.4% of momentum. We have gained 53.4 extra momentum, percent of momentum, which is a huge difference. Momentum is absolutely not conserved, way too much extra momentum. So obviously, that can possibly be correct. So this experiment must be wrong, done very badly. Okay, so we have 53.4% versus 6.9%. Now let's take a look at the kinetic energy. The initial kinetic energy is 0.044 joules, and part 1, when it bounces back, has a kinetic energy of 0.0042 joules, and part 2 after collision is 0.0369 joules. When we add those together, these are always positives because kinetic energy is a scalar. When we add them together, we have 0.0411 joules. The difference between 0.044 and 0.0411 is 6.6%. Okay. So for conventional physics, this is the total energy in a system, the kinetic energy. Okay. That should always be conserved. Now, of course, it is, well, theoretically, but it is normal. It is absolutely normal that within an experiment that after the collision, there's always going to be some loss of kinetic energy due to sound, heat, vibration, etc. There's always going to be a little bit of loss. So it should be normal that the difference between the total amount of initial kinetic energy and the combined kinetic energy after the collision is going to be less. So we have 0.044 and here we have 0.041. So it's less than the initial energy, and that's normal. There is some loss. Okay, whereas according to the opposition, draft science mainly, kinetic energy, we should throw that away and we should only look at momentum. Momentum is energy. So there is a huge difference. The initial momentum is 0.156, and when we add them as a positive, so after the collision, the combined momentum is 0.244, way more momentum than the initial momentum. The difference is huge, so that's impossible. We both agree that free energy is impossible. You cannot have more energy than what is your initial energy. But the problem is, if you are going to treat momentum as a scalar and not as a vector, then we are always going to end up with more energy than what is the initial energy. And that's the big problem. Now, this is my 6th analysis video, and each time it has been shown that if we treat momentum as a scalar, that there's always extra momentum than what was the initial momentum, or always extra energy than what was the initial energy. Whereas for the kinetic energy, the combined energy after collision is always a little bit less than what was the initial energy, and that's perfectly realistic. There's always some loss of energy. Okay, so once again, so this is it. This is the 6th elastic collision, and now we're going to be, I'm going to stop here and I'm going to make another one. All right.